most of the reactions in chemistry are generally done in solution. And solution, as I mentioned earlier, is a homogeneous mixture of solute, component in the least amount, and solvent, the component in greater amount. The solution itself is a combination of those. Typically, solutions are expressed in concentration terms. Actually, it's the concentration of solute in solution. And concentration, therefore, is by definition amount of solute. That's the reagent, reactant, or whatever you're working with in the equation, like HCl plus NaOH. Well, HCl might be the solute, but HCl will be in a smaller quantity than, say, in water, which imbibes the solvent. Now look at what I'm about to write. Amount of solute and volume of solution. I did not say volume of solvent. The denominator is volume of solution. Okay, so it's a combination of solute and solvent. Now that'll come into play in the future, but not right now, other than to say that, make note that we're talking about solute dissolved in a body of solution. The body, solute and solvent. The most common term, concentration term, in chemical stoichiometry used is molarity. Molarity is not moles. Molarity is a concentration term. It's a density or distribution of solute in solution. And it's given by a symbol big M. And by definition, it's moles solute, which we know everything about now, over volume of solution, I put in parentheses, expressed in liters. So if you have so many moles divided by solution, total solution volume, then express it in liters and you'll get molarity, what it's called. It's actually a density number. Mass volume ratio is the distribution of solute in a given quantity. Say you're given 0.25 mole of sodium chloride in 250 milliliters of solution. What is the molarity of NaCl in this solution? And you just follow the definition. So molarity, M, is 0.25 mole divided by 250 milliliters, but that's not correct. It needs to be in liters, so you move your decimal 3 places to the left. Milliliters to liters, move 3 places left. Okay, 250 liters. And what I have 0.01 or something. Yeah, 1 molar. And it's 1 molar in NaCl. Now, the idea of saying 1 molar, it's kind of like, what does percent mean? It's parts per hundredweight, right? Well, when you see this term 1 molar, that means 1 mole per 1 liter solution. So, if you're just given a concentration term, what does it mean? Concentration is 0.75 molar sodium hydroxide, period. What does that mean? The terminology, big M, is moles per liter. It's always normalized to 1 liter. So this means 0.75 mole in 1 liter of solution. Now, if you have to calculate that based on data, you'll have to put it in the definition. Because sometimes they give you a smaller amount. Not everything doesn't come in 1 liter quantity, you know. So, but you need two things here. One, calculate molarity, given moles and volume of solution. And two, what does molarity mean? It means moles per liter, moles per 1 liter. And you can multiply, if that's sodium hydroxide, that's 58, I think. And so that's equal to 0.75 times 58 grams per mole per 1 liter. So what this will tell you how many grams you have per liter, if that's what the problem might ask you for. But that's not a common term. Yes, sir.
Is the NaOH, is that the
Sodium hydroxide.
or the solute?
No, it's always the solute. I'll always put the solute in there. Good point. It's solution, solvent, and everything we do in this course is going to be water. It's all of them going to be water. So when I get right out, a solution is 0.75 molar in sodium hydroxide. Yeah, that's the solute in 1 liter of solution. And so you've got the rest of it. You got, all right, well, that's a good point to make here. Let me do that out. We got 0.75 times 58. So we got 43.5 grams of sodium hydroxide in solution. Well, 1,000 grams is a liter minus 43.5, 956.5 grams is water, plus the 43.5 grams of NaOH. So together, they make up 1,000 grams. Well, 1 liter is 1,000 grams. In these kind of problems, we're not going to go to super concentrated systems. So it's 1,000 mil. 1 mil of water is 1 gram. So yeah, that's a good point to make, bud. Thanks. So you're given the following: 36 grams of potassium bromide was dissolved into 331 milliliters, dissolved into water to form 331 milliliters of solution. What is the molar concentration of potassium bromide? Applying to the definition of molarity, molarity is moles over volume expressed in liters. Well, what have you got? 36 grams. Well, that's the solute part of this. So you need to convert that to moles. Well, how do you convert that to moles? That's 80 plus 39, 8, 9, 11. That's 119 grams per mole. Right there. What I'll do is I'll take this 36 grams over 119 grams per mole. See how I converted the numerator there using the data? I take the grams, go to moles. Now the denominator is, this is your solution. Now it's listed in milliliters, so I want to move the decimal 3 places to the left. And so when I solve that, I have molarity. See how it's moles over liters, and it conforms right into the definition like that. So you'll see some problems pop up like that in the future. The solutions are a big part of chemistry, guys. Trust me. And so whatever that comes out to be, grams drop out and you have moles per liter left. And 0.914 molar. We'll tear it out. Whatever. Problem will read 25 milliliters of 0.35 molar HCl is mixed with 30 milliliters of 0.31 molar sodium hydroxide. Hey, what's the excess? What's the limiting reagent? Which is in excess and how much? That's a very important type of problem because many times you're pouring acid into the base and trying to come up with a conclusion as to, well, what's the pH after you mix those things together? And so this is a good example of that. One of them is going to be in excess, is going to dominate the pH. It's going to be basic or acidic in the context. Well, solving a problem like this, just like what we've already done, we convert to moles and solve it in terms of moles. Now this is a 1-to-1 reaction ratio in which we have HCl plus NaOH going to NaCl plus H2O. So it's a very fundamental type thing, and it's used extensively in acid-base reactions. Typically 1-to-1. Only get into the polyprotics, you get doubling your coefficients and what have you like that. But right now we're using 1-to-1 acid-base reaction as shown here. Okay, now the way I set this up is I illustrate only the reactant side as I build this. The way I do this is I put down my data, like this is HCl, 25 milliliters, and I put in parentheses the concentration, molar HCl, plus 30 milliliters of 0.31 molar NaOH, like that. Notice we have two items here in each case. That's solution data. Now volume plus a concentration term. A volume and a concentration term together constitute solution data. Now, with that, you need to be able to convert to moles. Because, see, we have HCl and NaOH, and we need to get to moles. So we can, once we get to moles, then we'll know who's in excess, because it's a 1-to-1. Smaller number is the one used as the limiting reagent. Subtract that from the excess, you know how much is left over. How do you get to moles? Well, I said earlier, moles in solution, I'll put it up here, moles is molarity times volume in liters. So what I'll do is I'll put another little pointy arrow there, and I'll convert that to liters. I mean, yeah, 0.025. I know that's in liters. That molarity, I don't have to do anything to. I just put 3.5 there, and then I'll put mole HCl. Molarity times volume in liters. I just followed my formula up here. And I'll do the same thing over here. I'll be 0.03 times 0.31. I'll say mole sodium hydroxide. And then I'll compute those two, and I'll have moles. You'll have the smaller number will be limiting reagent, and you'll identify the excess. 0.025 times 0.35 is 0.00875 mole. Look like an 875 mole HCl reacting with 0093 mole NaOH. So I've taken the basic problem that we're given, set it up against the equation, but I only note the reactant side because the product side is dependent on whatever the limiting reagent is anyway. There's no point writing it down right now. And so what do we have? Well, this is the limiting reagent, smaller number. So it's gone, but this will remain in excess. It's a larger number. It's by how much in excess? So we go excess NaOH is however much that is used up, because we're using it in 1-to-1 reaction ratio. So if I have 0.00875 mole of HCl, I'm going to use up 0.00875 mole of NaOH. So that's simply subtracting those two, 0.0093 minus 0.00875 mole of the NaOH in excess. Gives me 0.00055 mole NaOH excess. Now what's the concentration now? Ah, that was part C. That's what I forgot. That's a mole amount in solution. How much solution? Well, we mixed 25 and 30. That's 3, 4, 55 in 55 milliliters of new solution. That's what I say. A little more to this. So now the concentration, see the brackets, NaOH, that means molar concentrations. You'll see those brackets over and over and over. Means molar concentration. So I know I have 0.00055 mole in 0.05555 liters. I'm going to push it up. Mole per liter, and then when I normalize it, that is the denominator goes to 1, I'll have the concentration in moles per liter. That's 0.01 molar in sodium hydroxide after reaction stops. That looks like a lot of numbers and scribble it, but I didn't do anything other than show you how to convert to moles. And that's molarity times volume, right here. Once you got there, you compare it to the reaction. And then whoever's in excess, subtract the limiting reagent from it, and that tells you how much is left over. We'll do another one. "28 milliliters of 0.15 molar lead nitrate," that's a 2, is mixed with 22 milliliters of 0.18 molar sodium chloride. How much lead chloride is produced in this reaction? It's a double replacement metathesis reaction. Here we have lead nitrate plus the sodium chloride. Exchange goes to sodium nitrate plus the lead chloride, and that'll be one of the happy halides. That'll be your driving force. Come out as a solid. How much in grams of lead chloride will be produced from this solution reaction? So we're starting with 28 milliliters, and I'll put that in parentheses, of 0.15 molar. And I'll separate that one. And then we got 22 milliliters of 0.18 molar. And so, how many of that in grams? That's where we are. So the idea is to get these two to moles, right? How do you get moles out of those numbers? Molarity times volume in liters gives you moles. Okay, now we hadn't balanced the equation yet, I'm sorry. I mean, 2 there and 2 there. Okay. So we need to throw in, we got to find a limiting reagent and all that kind of stuff, right? Divide by coefficients and what have you I taught you today. So in this one, it's a 0.028 times 0.15 mole. Here it's 0.022 times 0.18 mole of the sodium chloride. And so molarity times volume. This one is 0.0042 mole. This one is 0.00396 mole. Okay, so we have a 2 to 1 ratio. So I divide that by 1, that by 2. So our division gives us, well, do it this way. This gives me 0.0042 against 0.00396 divided by 2. 0.00198. So, it's like that's the limiting reagent here. Smaller number. But we have to work it from this number right here. And this one's going to wind up in excess, but that's not part of the problem. The big issue is, did you understand how I got to the limiting reagent now? I converted to moles, divided by the respective coefficient. Smaller of the numbers is the limiting reagent. Now all I have to do is go over here. That's a 2 to 1 ratio. So how many moles of lead chloride did I generate? That's got to be a smaller number, right? Here's a 2 for that one, and that's a 1. By how much? I divide by 2. Actually, I got it right here. So 1/2 of 0.00396 mole of the lead chloride is generated, which is 0.00198 mole of lead chloride times its formula weight gives you the grams theoretical yield. And you calculate that. Lead's 207. 207. There's 207 and 35, 35, 70, 77, 277, okay? We come in here with 277 grams per mole. And we get 0.55, roughly 0.55 gram theoretical yield, what I got. Don't back me up. Oh, yeah. Yeah, there's a lot of numbers flying around. But if you keep your bookkeeping straight and realize that, well, let's go to moles associated with a reaction, solve that first. And then if they want something else later, we'll convert it back to something else. Remember, moles and solution data is always 2 numbers together. A volume number and a concentration number. And the product of those 2 numbers, molarity times volume in liters, always converts to moles, and then you can relate it to the reaction. We'll do that many times in the near future, because solutions are a big deal here in chemistry.